used more than one guess. Okay, so otherwise 2, 1 or more. Okay, but usually the open method should be more accurate or converse faster than the Bragton method. In the previous lecture also we talk one example about find, for example, the speed of the mass free filling from, for example, a certain position at the air, for example. So it fills, and here we have limitation for or boundation here for our graph. So to plot the function, we need to have limitation for our vector. This is my vector that I have, x. I should have a limitation. So here I have started from 4, finish with 20. After that, we decide our increment here. What's the increment that we need? For example, is the increment is 1 or 4? So if we reduce the increment, so we'll have more accurate graphs. After that, it's easy for us to determine the roots. For example, in this graph, they use increment 4. So the first one is 4, the second term 4 plus 4 will be 8. After that, 8 plus 4 will be 12, like this one, 16, 20. So this one. So here I should have 2 initial guesses. Okay. So between these two, I should guarantee that also if I multiply the function, evaluate the function at f of 4, multiply by the function at f of 20, this should be less than 0. Otherwise, this is usually for bisection. Okay, but here also we can guarantee if this is one term is above or below the x-axis. If this is not correct, for example, if this is greater than 0, so in this case I cannot guarantee I have roots here before I plot them. Okay, but this is not all the cases. Sometimes we'll see in the common figures, if we have f of 4 multiplied by f of 20, this is greater than 0, but we have more than one root, like this one. Okay, if I multiply here the function, now it is positive, and the function here is positive, and this is also positive, so multiplication will be greater than 0. So in this case, I have more than one root. Okay, so this method, it's not accurate. So we try to, we will use later, for example, the open method, for example, to find more accurate, or the method that's usually converse faster than the Bragton methods. So here, for example, in the graphical method, what we did in the previous lecture, we just plot the figure. After that, we look for the intersection between or the cross points between the figure or the function and the x-axis. So this will have roots at this point. Or by doing, for example, tabular method. Tabular method, we just have something like this one. We have table, and we do it, for example, using X, and instead we use, for example, a software, for example, MATLAB or Python or Java and others. So here I have the function. I define the function as we said. This is the function, equalize this to 0. Okay, and after that I substitute by the value of c to get the value of f of c. If I have change in sign between two evaluation, so in this case this will indicate I have 0 or root located between these two boundation. So as a result, so between these at least we have one root. Okay, what about? As a result, usually I will pick these two now. Instead to take this large boundation, I will take these two. And instead also to use the increment, because here in our analyze we do the increment by 4. I might decrease the increment to be by 1, for example, or 0.5. Okay, because we know from Taylor series, if we decrease the step size, we minimize the error. So here, for example, if we decrease, for example, the increment or the step size to 1, for example, or for example, 0.5, so our evaluation will be more accurate. Otherwise, you do this figure, for example, and in your software, you might decrease the increment. After that, you recognize this one. And so we said that this method is very, very simple, but in some cases, this will not. This method, for example, using this graph, the graphs, it's help us, for example, to see the behavior of the functions. From the graphs, it's easy to identify, but if you want to pick the exact value of the rows, we usually will get it. So, for example, in this table, I think we pick the value using this method, for example, 114.75, yeah? While the exact solution or the true solution will be 14.81. This is the true value, and this is the what we get by this method. So usually we'll have error between the true value and graphical method. So in this case, we want to have systemic method that will help us to find the exact solution or solution with minimum errors. So these figures, you can see these, for example, figures, we have different figures. By using the graphs, eitherwise by using the function, for example, evaluating the function at the lower boundation and the higher boundation or the upper boundation, we will see, for example, we have the same sign. Also, this is no rows here. This okay. But in some cases, for example, figure C, this C, I have the same sign if I multiply or evaluate the function at 4, multiply by the function at 20, I get the same sign, but here I have two rows. But if we use bisection method, this will inform us there is no rows located here. Okay, sometimes we have different in sign, but we have one root. Sometimes we have different in sign, but we have multiple roots. So in general, this method not accurate, but it give us or provide us useful information about the function. It might be a starting point for the bisection. If you want, for example, if I pick from this figure now, I have the error or the roots is located between these 2 points now, between 12 and 16. So I use this. So this will be my new initial guess to start the other method, for example, bisection or Newton method that we'll study today, inshallah. Okay, so this will help us to guess or initiate points or starting point for the other methods. So for today's, for example, using the softwares, as you can see, for example, this function we have here several routes, because any cross point, this will authenticate this will be routes here between at this point. Okay, so as a result, ya shabab, so they went for methods or systemic method that help us, for example, here to find the routes systemic. So one of these methods, as a practice method, we call this bisection method. The bisection method, usually it started from two initial guesses. So we have two initial guesses like graphical method. We have 4, for example, and this will be 20. So this is my initial guess. After that, we have the first condition here for a bisection method. We should have this condition to be valid. F of 4, evaluation the function at 4, multiply by f of 20. This should be less than 0. That means I have changed in sign between the upper limit and the lower limit. If this is not valid, bisection will not be applicable here. Because if I have f of 4 multiplied by f of 20, this is greater than 0, I might have one row, 2 rows, or 3 rows or more. Or sometimes no rows. But bisection will not guarantee the solution for this method. So the first condition for bisection, we should ensure that the evaluation of the function at the lower limit multiplied by the evaluation of the function at the higher or upper limit should be less than 0. So I have change in sign between the lower limit and the upper limit. This is the first step I should know. What after that I do, we compute the midpoint here. The midpoint between the two intervals. This is the midpoint, so this will be x at lower limit plus x at upper limit over 2. I compute new point at the middle. This, for example, 4. Here I have 20. I compute the point here will be 12. So after that, I will evaluate the function. If the function, for example, at lower limit multiplied by evaluation the function at the midpoint. So here I compute or evaluate the function at lower limit 4 multiplied by the evaluation of the function at midpoint 12. I will check this value if I have change in sign here. If this is negative, sorry, if this is negative or this is, let's put it, for example, general, this is less than 0, that means the roads that I'm looking for, it's located between these two. It's located here. And just I will ignore this interval. I will ignore the upper interval. I will consider only the lower interval. After that, this new interval, I will rewrite my new interval now becomes from 4 to 20. I will compute the midpoint again. And after that, I will evaluate the function at the lower boundation or lower bound with the new midpoint. I will check this condition. If this is greater than 0, if I evaluate it here, this one is greater than 0, so that means the roads now not located at this boundation because we have here both are the same sign. Because here x of L or x at the lower bound and x at the midpoint has the same sign. That means there is no road between them. Otherwise, both points above the x-axis or both points below the x-axis. So there is no cross point between. So in this case, I just, if this is greater than 0, I will ignore this one. I will consider this one. So only I have this solution now. I will start from. If I evaluate the lower bound multiplied by the midpoint and I find this equals 0. So here I will terminate my computing. I will stop here because f of r or r is exactly the routes that I'm looking for. Okay, شباب. Any question, شباب? Please.
ايوه دكتور.
في أحد موجود في الكلاس؟ نزلته.
موجودين. اسمعني دكتور.
يس.
موجودين بس دكتور ما عندي كويستشن صراحة. أحس واضح بالنسبة لي.
Okay. بسم الله خاتم الله. Okay, so if we do this example, for example, just review it because this is very important usually. Here, for example, we start from this practice. We have lower bound and the upper bound. After that, we compute the first step. As we said before we start, we evaluate the function at these 2 points. Okay, so here we have 12 and 16 evaluate the function at these 2 points. This should be negative to start the bisection. Okay, this should be negative. Multiply f of 12 multiplied by f of 16 should be negative. If it is negative, I will compute the midpoint. So here is 14. After that, I multiply f at 12 multiplied by f at 14. Okay, so I will evaluate this one. I find it positive or greater than 0. That means this is 12 and this is 16. I have here 40. If it is positive, if I multiply this one, the function at this point and the function at this point, this is positive, that means the ball would not, or the root will not here, will not include here or not exit here, so it should be here. So here what I will do, I will replace the lower bound by the midpoint. So lower bound now, or the midpoint becomes now lower bound, like this. I will have now two new bounds. This is 14 to 16 now. I will compute the midpoint, 50. Evaluate the function at 14 and 15. Because 14 you already compute, you will evaluate it at 15 only. Okay, so you will evaluate it once only. Evaluate it at 15, and I found the value is negative. So here I have this is 14 and this is 16. And the midpoint we said this is 15. If I evaluate the function at 14 multiply by the function at 15, I get it negative. That means I have change in sign here. So I will ignore this bound now. I will ignore 16. This is 15 now will becomes my upper bound. And my previous or my current lower bound will still the same. I will do it the same algorithm. I will continue with this one. Okay. Sometimes, for example, during our steps, otherwise we'll determine the number of iteration that we need, or based what's the stepping criteria, or based on the error or the value of error we stop for. Okay, Shabab. So the approximation error here, for example, approximation error that we have, it's equal the current or the present evaluation of the midpoint minus the previous estimation of the midpoint over the current estimation of the midpoint. So the midpoint actually it's determine the routes that we're looking for. This is the routes that we're looking for. If we increase the number of filtration, we will have or we'll have, so for example, sum of decimal or significant figure or the same significant figure, or for example decimal places as well. So going with increase the number of alteration, we will go near to the exact solution. So the algorithm that we usually use, as we said, we have this, the function should be continuous, and we should have this function. Choose random, for example, guess for lower bound and upper bound. It should be practice. We should have the function, if we evaluate the function on this terminal, this should have with opposite sign. Opposite sign, that means if I multiply f at xl multiplied by f at the xu, so in this case I have negative sign. Otherwise I will stop my iteration here. Second step, I will estimate the midpoint, okay, r. After that I will use my algorithm. If the function, for example, at lower bound multiplied by midpoint is greater than 0, less than 0, so I will set, for example, x of u equal x of r. If a function at lower bound multiplied by the midpoint is greater than 0, I will set x of l equal x of r. If the function at lower bound multiplied by the midpoint equals 0, so in this case stop or break the alteration, and I will set the root is equal x of r. Okay, so here, for example, also we might have the estimation, for example, here to calculate the error. Okay, so here the present value minus the previous value over the present value multiplied by 100%. So after that, we compare this with the stopping criteria. If we want, for example, to stop, otherwise by the number of iterations, or by we satisfy the error that we want to compute. Okay, شباب. So stopping criteria that we have here, we have different stopping criteria for bisection method. Usually, we should guarantee that the error is equal or less than b, the upper boundation, minus lower boundation over 2 of power n plus 1 in just the number of alterations. So if I want to know, for example, if I want how many alterations I need to stop, for example, if the error equal a certain value. Okay, so I need, for example, to know how many alterations I want to stop, for example, if I know the value of the error or predefined value of error. Okay, so what we do, just we apply logo at both sides of the equation. So I apply logo, so I will take logo here of the error and logo for this term. Okay, so we get this formula now. So here, for example, the number of alterations, it's equal logo of the difference in boundation, the lower, the upper minus the lower, multiply here usually without no need for this one. You'll see this minus the logo of the error over logo of 2. Okay, so we find this one. So here, this is the function that we want. This is the upper and the lower bound, and this is the value of the error. So if you look for this one, so let's take this example here. The error here, it's equal, for example, if we take the lower boundation and this is the upper boundation and the lower boundation, and it's given the error. Okay, given the error. And here I will check this one. I think in the book we don't have 2 here. But I will check it. Okay, for this to multiply by the error, I will double check this formula before I resubmit, because what you have in the hand in the lecture, you have that the traditional one that usually we submit, or the coordinated one we shared before between all the classes. But if I add examples, for example, in the handout, and this handout is different from what I will submit, I will open a folder. I will call these slides or notes or something like this, because I will, if I get any new examples, I will add it, inshallah, more examples on these handouts that we have. Okay, so what I submitted on the Blackboard sometimes different from what I have, because during my preparing, if I get an example new, I add, just improve, try to improve more. Okay, so you'll find this is my different from a little bit different, not يعني big difference between, just I add one example or 2 example or like this one. Okay, شباب. So after this, inshallah, I will submit this new one, for example, in the hand or the notes or the handouts folder. Inshallah, I will create it later. So here, let's take this example, include 2, but I think it is without 2 in the handouts. If we check it, I will check the textbook later. Okay. If we look for this one, you see how many alteration are needed, just that the error will becomes 0.005. Here, for example, it's given the lower boundation and the upper boundation that we have, 6 and 7. So what we do, we just take logo for the difference minus logo for 2 multiplied by the error. So after that, the difference here would be 1 minus 0 or 1 over log of 2. And this becomes 1999. Okay, and this we said this should be greater than, so we just make it this number, for example, or around this to 10. So the number of alteration that we want, it's greater than or equal. So the minimum will be 10. So to have error less than this number, we should have 10 alteration or more. Okay, 10 alteration or more here. Okay, clear this one يا شباب? Yes. Yes, okay. Because what we have here, this? I will check this one, because here what we have in the comment slide, I have here the error itself. If this is the approximation of the error, and here we have the error without 2. So I will revise what we have in this example.
Doctor, for the error here, it is approximate error, not absolute error, right?
Yes, the value of the approximate error.
Even for the previous one, the Newton method.
Which one?
Yes, okay, it's the same.
Yeah, the same things here. For example, how many iteration, or to check the number of iteration that we want, if it is give us, for example, the boundation, the upper limit and the lower limit. Here I have 16, and here I have 12. And to get the approximation error, it's equal this number. Okay, it's equal.
We can find it even if it's not mentioned.
What's
the approximate error? We can find it.
Yeah, if you have the alteration, you can find it. You can do it the opposite way. Yeah. Okay, so if I do how many iteration, for example, if I give you the boundation, for example, the upper limit and the lower limit, and give you run this algorithm for 6 iteration, you will have estimation for the error, because just do the opposite here. You have 6 here. Take a logo, and this is unknown. You can know what will be the expected value of error. Okay, the expected value of error. So we do it in this way or another way. Okay, شباب. So that what we have, the error is what we need here. The error that we compute, it's equal the exact solution over, for example, the error that we estimate over 2. Okay, so here we have the boundation, or what we call this B minus A, or the other boundation of the system, or the last boundation of the system. So this is B minus A. This will be the lower boundation. If you do, for example, algorithms here, step by step, let's go here. Where is the table? We have to. Yes, for example, this table, for example, what will be the last boundation that we have? Okay, this is, for example, boundation. I have here, for example, the upper bound is 14.875, and the lower bound I have 14.75. So here we take B minus A over 2. Okay, so this is usually the error that we want to compute. Okay, so here what we do also, the same things here. If you want, for example, to compute the error, the approximation error will be 14b.875 minus 14.75 over 2. So this will give us the approximation error that we want to stop.
Doctor?
Yes.
2 in the denominator from the
Which one?
formula, or the number 2 in the denominator?
No, this is the error between 2 points, because here we take usually the midpoints, so we take the difference. We have B over A. This is the formula that we have to compute the error. Yes, this is the formula that we have.
Okay, clear.
Okay, and the formula also we prove it based on this one. And the formula, if you look for the formula that we started from, we have also the same things, but here, if you want to determine the number of alteration that we have here, see this one. Here we have B minus A over 2, but here it's dependent on the number of alterations, how many alterations that we have, because here we want to put it in general form. Okay, so even to do how many iteration, we just put the number of n here. But for example, in our table, if you want to compute the error, for example, not percentage approximation error. Here, this will be b minus a over 2. If you want to compute the percentage, usually we take it like this. This is the percentage error. Okay, this is our percentage error. But do you want to guarantee our converge of the system? Usually, we consider the stopping criteria based on the percentage error, because the percentage error will give us more meaning, better than this value over 2 of the error. Okay, so better to consider this as stopping criteria for you. Here is clear يا شباب البايسكشن method. Bisection easy يا شباب.
Yes. Okay.
Okay, so here we have another examples for bisection and exercises inshallah. I will look for this later inshallah if I have time. Okay, I will post this one. So here, for example, I want to show you this example usually from the previous term. Sometimes in the exam this comes. Can you use bisection method to find the zero or the root? Sometimes we call in control we call this zero and poles, but here, for example, in general, let's say a root of this polynomial in this interval, from 0 to 2. Okay, so as we know, the first condition that we have, I have to evaluate the function, lower boundation, our guess, and upper boundation, our guess. This should be less than 0. But here, if I evaluate the function at these 2 points, I will get this equal 3. And this is greater than 0. So in this case, our assumption is not satisfied. Otherwise, we need to change the boundation here or here. So in this case, for this type of problem, I will stop here. I will say this method, it cannot be used. For the bisection method, it cannot be used because the first condition not valid. Okay, the first condition not valid here. Any question? So this bisection method, this algorithm, inshallah, I will post it. Algorithm using MATLAB for bisection method. How we do the algorithm, inshallah, I will post it, inshallah, on the Blackboard. You will go through this one. So notes on bisection method. Bisection method, most robust route founder, least efficient, guaranteed to find a route as long as the boundation cross x-axis. For example, we have change in sign. Okay, if there is no change in sign, sometimes we have 0 route, or sometimes we have even number of routes. Okay, a change in sign will add or will inform us we have at least 1 route between these boundations. And what we want to consider also today, we'll talk about the open method. Open method, it's different from the Bragton method. We said the Bragton method, we bracket our boundation 1 and 4, for example, at the beginning. After that, we start from these 2 initial guesses. The open methods are started usually from 1 or more initial guess points. So in each iteration, a new guess of the route is estimated. So usually the open methods are more efficient than the Bragton methods. And they may not converge to the route. Sometimes this is also the problem with the open method. During this chapter, we will study 2 basic methods, a Newton-Raphson method, and the second one, secant method. And after that, we look for modification to these 2 methods to solve the problem of multiple routes. Instead, we have only 1 route, so we need some improvement to these two methods to solve the problem of multiple roots. Just we do modification to these two. So the open methods are based on format that required only a single starting value of x, or sometimes two starting points, like for example second method. Newton-Raphson method, it's need only a single starting point. These values does not necessary to be bracket or bracket. So what's Newton-Raphson method? Newton-Raphson method, it's a formula derived from Taylor series expansion for linear system, first order derivative. Okay, so if we have this is Newton or Taylor series expansion like this one, we still remember this one. This to protect the value at xi plus 1. This is the function at xi. The first derivative multiplied by step size, and this is we goes with highest order. Here, for example, in Newton method, we usually look for linear equation. So in this case, we will omit the non-linear terms or the highest order. We take only the first order, like this one. So this is will be the first order expansion that we have. After that, because we look for the root, and the root is the intersection between the x-axis and the function itself. Okay, because this is the function that we have, and we look to the intersection at this point. Intersection, because we look for the root at this point, f of xi plus 1 should be 0. F of I plus 1 should be 0. So in this case, I will set this 0. I will get this formula. So by reordering this one, because I want to find the value of xi plus 1. So you will have this form of the Newton-Raphson method. So this method now, it's help us to find the roots. So it is equal, so this is the new root or the new estimate, and this is the initial guess xi. I have the function at xi and the derivative. The problem with this method is to find the derivative of the function. So for each step, we need to find the first derivative of the function. After that, we evaluated each alteration or every alteration. Okay, so here this will be our new estimate of the root. This will be the previous estimate of the root or the initial guess, and this will be the evaluation the function at xi. This will be the evaluation of the first derivative at xi. So this is the formula of the Newton, or we can get it from the slope. Okay, from the slope here, if we take this is if we have here the slope, we have this slope, for example. This slope, for example, at xi, this is the function at xi 1. Okay, and we know this is equal 0. We know this is equal 0, so just multiply both here. I have xi. After that, by rearrange the equation 1, so I will get this formula. So this is my initial guess that I have, and this will be my new estimate of the root. Okay, this is my new estimate of the root. As we said, the problem here with this method will be the evaluation of the or computing of the derivative. Sometimes it's very, very difficult to find the derivative of some functions. Okay, sometimes the derivative also equals 0. If we have some function, the derivative of the first derivative of the function might equal 0. So in this case, this formula will not be applicable. Let's take example. After that, inshallah, we'll understand this one. Find a 0 or a root. We call this root because we usually we do this for control side. I will say this, find the root of the function f of x. Okay, and this is the function that I have. And starting from this initial guess of the root. So this is the initial guess or initial estimate of the root that we have. So based on the Newton formula, let's pick this formula here. We'll pick this one. We'll put it here. Okay, so this is our logarithm now. Okay, so alteration, for example, the first alteration, if you start, for example, you can say this is alteration 0, okay, or alteration 1, you might have here xi, this is x0, okay, this is x0. So let's write to be clear. I'm sorry, confusing. I will erase this one. This is I minus 1 should be. This is minus 1. نصير confusing في logarithm. Okay, so here I have xi minus 1. Evaluate the function at xi minus 1. Evaluate the derivative at xi minus 1. Okay, so here يا شباب, this is what I do. The first thing, so I have to get the first derivative of this function. This is the first derivative. I just derive this one. I have here cubic will be 3x squared minus 4x plus 1. This should be equal. Okay, so this is the first derivative. For the first alteration, I equal 1. I can say I equal 1. After that, this I equal 1. Substitute here. I have I x equal 1. So this will be 1 minus 1 will be x0. I will look for the value of x0. So the value of x0 is 4 over the function here at x0 is 4. I just substitute here instead of x by 4. Okay, using my calculator, I will compute the value equal 33 and evaluate the derivative at 4, and this also equal 33. Just I solve this problem, I get the second estimate or the first estimate is equal 3. Here, for example, if you want to compute the error, you might compute, okay, or you might compute the estimation here between this one and this one. Now this is becomes x1. So here my iteration I equal to. So here x2 is equal 2 minus 1 will be x1. So here will be x1 f of x1 over first derivative of the function at x1. x1 equal 3. Evaluate the function at 3, and when x equal 3, and here evaluate the derivative when x equal 3. I will get the new estimate of the root equal 2.4375. After that, I will use the third alteration like this one. The third alteration now, x3 is equal x2, a function for x2, derivative for x2. This is x2, and this is the evaluation. This will be the value of x3. So I will continue like this one. So this will be the new estimate now. Okay, I will continue doing estimation يا شباب until I have some stopping criteria. Otherwise, for example, the number of the question, for example, determine the number of alteration that we do. So, for example, we sometimes in our exams we said do these, for example, for alteration, for example, or 3 alteration. Okay, so do these, for example, for 3 alteration, or for example 4 alteration, or stop, for example, when the relative or percentage relative approximation error, for example, with certain foundation. So we have different criteria. Sometimes we determine the number of alteration that we want. Okay, so here, for example, we do 3 alteration. We have this one. Let's look for the solution of this problem. Here, for example, we do here 4 alteration. So this is xi's. This is the estimate of the error, and this will be the approximation error, not the relative. Okay, this is the approximation error. The difference between the present and the previous estimate. So this is the previous estimate for, and this is the current estimate. Okay, so this is the current estimate that we have it here. You can see, يا شباب, the error goes to 0 or converge. Any question here, يا شباب? Any question here?
واضح دكتور.
Okay, so the problem, يا شباب, here is the derivative. If it is easy to compute the derivative, so in this case the problem also will be easy, and the logarithm of this method easy as well. This is example from the textbook. I hope you get the textbook. They sent the textbook for you, يا شباب, or no?
No, not yet.
خلاص. I shared with you, يا شباب, a line صح, our time for the midterm, yes. I think will be 10th of July. Yes, yeah. I have another course, yeah, 5th of July. This before the break. Before the break. Okay. So this is another example from the textbook that you have. If you need, for example, to share, I have chapters from this one. Inshallah, we'll see how, or handouts from this one, or lectures from this one. If you want, for example, you can ask me. Inshallah, I will send it. I will share it with you. Here, for example, use Newton-Raphson method to estimate the roots at this one. So you have here the initial case, and this will be the solution of this one. So this will be the estimate that we compute. Okay, this is the estimate. We started from 0. This will be the new estimate, and at second iteration, the fourth iteration, like this one. Okay, and the true value here, you can see this is 0.5671439. So here the error, the true or relative percentage true error, it's equal or less than power of minus 8, 10 of minus 8. Okay. So this algorithm, Shabab, is very easy because we have only 1 point for each iteration. But here the problem is the first derivative. If you can compute the first derivative correctly, you should evaluate this correctly, Shabab. And you should practice this for ln, cosine, sine, for exponential. This is the function that usually we have during the exams. Okay. Problem, Shabab, with the Newton method, usually, because how we do this Newton method. Okay, so if we have graphs here. Okay, let's have it graphs here, better graphs here. Yes, let's take one of these one. Okay, so usually, Shabab, if we do, for example, Newton, we do, for example, tangent here. Okay, or the slope. We draw the slope here, for example, for this point. I started from this initial guess, x of 0. After that, if I went, for example, to use the tangent here, the cross point between this slope and x-axis, this will be my new estimate that I compute, xi plus 1. Okay. After that, I will draw this point here. Okay. After that, I will draw a slope or tangent point. So let's take it like this one. Like this. So if I start from here, I will draw this tangent like this one. This is my starting point, xi0, and this low. This will be a new estimate. After that, I will draw this point here. I will draw a slope like this. I will cross here, for example, x2. Okay, until I reach this 0. Okay, so after that, I will draw this figure. I will compute the slope here, like this one, until I reach, for example, or becomes near to the road that I want to compute, like this one. The problem here with some types, the slope will be parallel, for example, or constant, goes, for example, to infinity like this one. So if we have at some functions, the slope will goes infinity, and not, for example, converge to the correct, for example, roots. Also in this figure, for example, in the problems usually when we have optimization, minimum or maximum, so usually the slope will goes constant like this. And sometimes also the slope will ignore, for example, what we call this the correct route, and will goes, for example, away from the route that we have, because we depended here on the evaluation, the value of the functions. So the problem will be more efficient if our guess is close enough to the sample route. This method will be perfect if we close enough to the sample route. So in this case, the method will guarantee converge quadratically. Okay, so we'll converge faster to the route that we want to compute. But if our first guess is far from the sample route that we want to compute, sometimes the Newton method will not converge to the correct route. Also, the problem with the Newton method is run away, like this one. The estimate here of the route is going away from the route. I start from this initial guess, and after that we should have the initial guess at this point. The slope comes at this point, but the slope is running away from the route that we want to compute. So it's pick up another route away from this one. So we call this runaway estimation. Okay, or my estimation or our estimation run away from the correct or the sample route that we want to find. Because this is based on the evaluation of the function, and the derivative at point is far from the route that we want to compute. Sometimes we call this flat spot when the derivative equals 0. So in this case, our algorithm will fail here, or fails, because we have f of x over f of x over f of x over the first derivative. Okay, or sometimes also the first derivative value is very small. So in this case, the new estimate will be very far from our estimation. Okay, if the value of the derivative is very small, so here, for example, this is xi, and this is equal x0, and we have here the function itself at x0 over the first derivative of x0. If this value is very small, so in this case, this will goes, the value here will be very large. Okay, the value is very large. So the error between this value and the initial guess will be very large. Okay, so in this case, our estimate will be very far from this one. Okay, so we have different problems with Newton methods, and also the last one we might say sometimes we have the logarithms is rotate in one round. Okay, and rounds, for example, in this case between the two routes. Okay, so like, for example, if we have function like this one, so we guess from here will come at this point, and we also estimate like this one. So we might have logarithms will be circles, rotate like this. Okay, or take more time, for example, estimation and the same foundation. So this is usually the problem with the Newton. So the main problem with the Newton will be the derivative, the first derivative, by computing the first derivative of this one. So notes on the Newton-Raphson method. One advantage is not required two initial guess, it's need only one. Also, but here it requires a good estimate. So this estimate should be close to the root. If it is far from this one, sometimes it will not converge. Also requires the evaluation of the function at f of x. For all the methods, we need this f of x, and also the first derivative. We should have the first derivative of the function. This will converge extremely faster if the function or we start from near to the correct roots. Sometimes this method will converge to a wrong root if multiple roots are exit. So the problem here also we have another problem with the Newton method will be multiple root exit. Okay. So let's introduce the third method or the fourth method, second method. And this method usually it is just a development of Newton-Raphson method by ignoring the use or by approximate the first derivative that we have in the formula by put it in a finite difference form. Because as we know, one problem in the Newton will be the derivative here. So here, this second method just approximate the derivative by use the finite difference. And we know this, the first derivative is equal the slope, and this will be the finite difference. It's equal f of x I plus 1 minus f of xi over xi plus 1 minus x of I. So we just substitute this one here to get the new formula of the second method. Okay, second method here, it's equal this form, but here the problem also with the second method, we return back, we need two initial guess, not one. We need two initial guess. So here we have the initial guess one, the first initial guess, and this will be the second initial guess that we want. Okay, so this will be the second method, inshallah, that we will study, or the second open method. And we call this also one of the good methods that we'll use, inshallah. As we said before, the problem with the Newton will be the derivative. So we solve this problem by develop this second method, and this will be the form of the second method. So if we have this is the form of the second method, let's do this example. The same example what we have before. Use the second method here, second method to evaluate or to estimate the root of x, f of x, exponential minus x, starting from initial guess. We have here two initial guess now. X minus 1 equals 0, x0 equal 1. So we have two storage initial guess, initial condition that we have. Okay, and the true value is like this one. So what we have here in the first iteration, so this is my first iteration. I have this is the initial guess, the first initial guess, and this is the second initial guess. Okay, so the iteration here, when I equals 0, put I equals 0. Okay, so here will be xi or x1. This will equal x0. Okay, so for first iteration, I have x1. This will equal x0 minus f at x0. I know the value of x0, just I write it here, this one. Multiply. So here I have x minus 1, this one, minus x0 all over, okay, f at x minus 1 minus f at x0. I will evaluate this function. So I have the initial guess, two initial guess. I have this is x01 minus f of x0 will be minus 0.63212. multiply by 0 minus 1 over 1 minus this function, and this will give me, this is the first estimate of the root. So here we might compare this with the true value. The true value, I have it here. This will be the first estimate. The percentage true error is equal 8%. For second iteration, or I have here I equal 1. So in this iteration, I type it. So this will be 2 equal x1 minus f x1, okay, multiply by x0 minus x1. This will be over x0 minus f of x1. Okay, so usually يا شباب we just to evaluate two terms here, this term and this term, or one term. You can see this term for each iteration, because this one is given from the previous one. We computed in the previous one. Also, f of 0 we computed in the previous iteration. So for new iteration, we need to compute f of the previous, or the new estimate. Okay, so here we just compute the second estimate of the roots, and we find this one, the value, and we might compute otherwise the relative approximation error, or the percentage true error, and the error is reduced. We also do, for example, the third iteration and the first iteration until we stop at a certain criteria. Any question يا شباب? Any question here?
All clear.
Doctor, this method is like the Newton, but the difference is we don't have first derivative here.
Yes. The difference between second, we replace, or we substitute instead of the first derivative by this coefficient. By this one. We don't have, no need here for the first derivative. It is the same criteria of the evaluation. So here we start from this one. We use the tangent gate here, for example, to estimate the current estimate, like this one. After that, we use this initial guess and this guess to draw a slope. After that, to estimate the new value like this. But here, we don't use the derivative, the first derivative, and also we have two initial guess in the second method. Okay, شباب. If it is clear, please do for me the fourth iteration. When I equal, this is I equal 2, do I equal 3. If it is clear. You have 3 minutes. If you, yes, if you solve it, send it by WhatsApp, okay? With your ID.